So we'll now be discussing the kinematics of a point in path coordinates, and by point we mean a material point in a body, in a rigid body, of course. So just to recall, the Cartesian and the cylindrical systems which we had learned were called extrinsic coordinate systems. Okay, because the coordinates were fixed beforehand. Okay, this particular topic, which is path coordinates, in this you will see that the coordinate system is determined by the path of this moving point. Okay, so it's not fixed beforehand. So let's see how that looks like. I'll have to draw another diagram. Okay, I claim by drawing a nice diagram, but I hope it's understandable. That's the most important part. Okay, so let's have this. Okay, let's have this is the path. You have a frame F. This point is O. The position vector of this point is P of S. S is the path. Okay, and hence this would be called R of S. Okay, let's see. So S of t, which you have over here, is the coordinate along the trajectory of the moving point P. At time t. So we want to make our coordinate system now. Okay, so you will have a, I think I should just call this somewhere else. Maybe let me just put it over here. So this point is P over here. Let me draw a coordinate system, and that would be En hat at this point. Okay, then you can have Et S, and then there will be one which will be inside your screen, that is EB of S. Okay, angles are all 90 degree. Okay, angle between En and Et is also 90 degree. I am just not making that because we have a lot of things to do over there. Okay, so this is a right-handed triad of unit vectors Et, En, Eb at the location S is shown in your figure. Okay, and you can say that ds square is equal to dr dot dr. Okay, and this would be equal to dr by ds into ds dot dr by ds into ds. Okay, so let me just show what this ds and dr are. Okay, so this is at point P over here. Now the next point where it is say over here. Okay, let that point be called P dash. Okay, and hence we can draw another position vector that would be called now what? R of S plus delta S. So delta S clearly is this. Okay, this is delta S. This small change in S position is delta S. So that is how we have written that delta S will be shown, and ds clearly is an infinitesimal change in the position. So when delta S tends to 0, that becomes a ds. Okay. Now if we want to write this ds square, that can be written as dr dot dr. Okay, and this can be written. So how can this be written? So let's see, you will have a delta r, sorry, delta r will be equal to r of what? S plus delta S minus r of S. So when this limit tends to 0, it becomes a dr. Okay, limit delta r tends to 0. So when delta S essentially tends to 0, this becomes dr. Okay, so you can clearly see this triangle which has r of S plus delta S and r of S and delta S, and you can use the vector relationship in this triangle and find out that ds square will be equal to dr dot dr. Okay, now once this is written, you can imply from this that actually dr by ds modulus is equal to 1. Okay, because you know that this dr can be written as this. Okay, again it's not a division or multiplication by ds, so I hope this concept is clear. Why are we writing it like this? Okay, so since it is equal to, so ds dot ds will be actually equal to ds square, so this squared will be there, and hence the only possibility is that this is true. Okay, so I mean if you write for example the dot product, that becomes dr of ds into ds. Okay, then this will be squared and this will be squared. Okay, and cos of the angle between itself will be 0, so it will be equal to 1. Okay, so that's why we are saying that the modulus of dr by ds is equal to 1. See that dr by ds can actually be equal to minus 1 as well. That's why we are taking the modulus. Okay, let's now see and claim that et, you see et over here, the green. Okay, this is the tangential to en. So let's say et is equal to dr by ds. Okay, this is a small change in r with s based on this diagram which you have, okay, in the tangential direction, and this can be written as delta s tending to 0, where delta r by delta s is there. Okay, so this is actually defined in this form. Okay, so the tangential unit vector is defined over here like this, and it is in the direction of increasing s, Let me just write it like that. So as you can see, as s increases from p to p dash, that's the direction of et. Okay, et hat. And this is also physically, you can see this, or visually perhaps, that's the more correct word. Visualize this. As delta S tends to 0, the direction of chord delta R, okay, becomes a tangent. At where? At S, right? At this point P, where P is. So at that particular path coordinate S, this becomes tangent in the limit when delta S tends to 0. Now let's also see what d by ds will do to et hat dot et hat, and this is equal to d by ds of what would be this vector with itself, that would be equal to 1, and hence this should be equal to 0. Okay, you can also use this by the chain rule. Okay, so you can apply the chain rule over here. So it will be what, det hat ds et dot et hat plus et hat det hat ds. Okay, now this will be equal to, this particular term will be equal to det hat ds dot et. So overall this becomes a 2 times of 2 times of this becomes 2 times of det hat by ds dot et hat equal to 0. Okay, and this is 0 because you have already shown this to be a 0. What would this imply? Well, clearly 2 is not equal to 0, so the only possibility is that det of by ds is actually perpendicular to et, if obviously det by ds is not equal to 0. Okay, so et hat cannot be equal to 0 because it's a unit vector, it has a magnitude. So the only possibility could have been that if this det by ds is equal to 0, but since we are ruling that out, we can say that det by ds is actually perpendicular to et. Okay, now we'll be able to use this very soon in this statement. The unit vector En in the direction of det by ds, okay, if det by ds is not equal to 0, is defined as the principal normal vector of the curve. Okay, now since dn and en and et are perpendicular to each other, okay, and here you have found out that det by ds is also perpendicular to et, okay, So you are saying that the unit vector En in the direction of det by ds is defined as the principal normal vector, that's En, okay, of the curve. But the thing is that there are actually infinite set of unit vectors which are perpendicular, right? Like you look at this diagram, okay, En, so once you say have a Et, okay, then En is perpendicular to Et, that can be shown, but En can have infinite ways of existing so that it is still perpendicular to Et, right? You can rotate it about this point S and it will always be perpendicular to Et. So that's where this next statement comes in. Sorry. Okay, so defined as the principal normal vector of the curve, there being an infinite set of unit vectors normal to the curve at P. Okay, so there is infinite possibility for sure if you see just the perpendicularity between Et and En. Okay, and direction is clearly given of En, that is of the det by ds according to this definition and based on the derivation which we have just done. A couple of more definitions are thrown now. The magnitude det by ds is defined as the curvature one by rho, and rho is called the radius of curvature. Is curvature at P. Okay. Done. Okay. Okay. So clearly, En is normal to Et and directed towards the center of curvature C, where RC is equal to RP plus rho En of the curve. Okay, so just to revise and correct a mild note, that yes, En, a finite set of perpendicular vectors, okay, which have magnitude which in the direction of det by ds can exist at this point, but we call the one which is normal such that it is directed towards the center of curvature. Okay, that point, and I'll show you over here, is somewhere like this, C. Okay, so now it is fixed. Now you cannot have, so out of those infinite normal vectors which you could have had, there is only one which will be directed towards the center of curvature. Okay, and that is what you call as En. There are many principal normal vectors here. Where did you go? There are many principal normal vectors, but only one of them will be called En for this case, the one which is directed towards C, okay, which is the center of curvature. So The other thing which should be done now is to draw a vector like this, that is called RC is equal to RP plus rho En. Okay, so I hope you can see why this is called Rp plus rho En. So this is clearly Rp, okay, and this whole vector from here to here, let me just show another ink. This whole vector from here to here, okay, sorry, this is rho times of En hat, because En hat is a unit vector. So I'll just now remove this. Okay, so this is Rc equal to rho Rp plus rho En. Okay, and clearly there is a circle associated with it. Okay, since it's the center of a circle, center of a curvature, so we must show that circle. So I'm trying to draw, so C to P is the radius, and let me draw one circle. Okay, not the ideal circle, but I hope you get the idea behind this. So this is called the circle of curvature. Rho is called the radius of curvature. Okay, that's how we were saying from here to here is this radius r, that value is rho. Okay, so that's where we say En is the normal to Et and directed towards the center of curvature C of the curve. Okay, and so this implies that dEt by ds is actually equal to 1 by rho En. Okay, just because En is directed towards dEt by ds and its magnitude is rho. Okay, so that's how we can write this, such that. Okay, now you can have, to complete a triad, obviously the third leg has to come in now, that would be Et cross En. Okay, this is called the binormal vector. Actually, I refrain from using the word that this binormal vector EB, which you see this green dashed line, okay, over here, this is inside the screen. I don't want to say that because that would mean that this curve, this path is on the screen. But the whole point of studying this subject is this path S is three-dimensional, and hence to say that EB would actually be inside the screen would be wrong, and that's why I am refraining from saying that right now. I hope you can understand why. Okay, so EB, yes, EB will be ET cross En, and if it is all in this one plane, then EB will be inside the screen. But since this S is actually a three-dimensional curve which is being drawn on your screen, we can't really make very strong comments about where it will lie on the screen. Okay, so let's now sort of revise all the definitions which we have had. We had ET is equal to dr, sorry, by ds is equal to limit delta s tends to 0, delta r delta S. Okay, then we have det by ds is equal to d2r by ds square. How do we know? Just differentiate this with respect to s, okay, and then you should get a d2r by ds square. This was shown to be equal to 1 by rho en hat. Should put a en like this. Okay, and eb is equal to et cross en. This is 1.22. Now we also say that et cross en is equal to eb. I should not be using this. You are free to use the overhead arrow. It's just that I am so used to a hat that I have to make them wear a hat. Okay, and then en cross eb would be equal to et. This is a standard triad relationship. Et hat equal to en hat. Now one can say that 1 by rho is equal to d2r by ds square, okay, from this relation. Sorry. From this relation, okay. If you remove the direction part of it, you will say that the magnitude of this is equal to 1 by rho, okay. And how can this be written? This can be written as dr by ds cross d2r by ds square. Okay, how can this be written? See, this is equal to et. Okay, I should not be using this. This should be, yeah, why am I getting this color? Okay, so we have this as et, okay, from over here, and this thing is actually en, right? So we can say, or en by en by rho, right, 1 by rho. And if you take this 1 by rho out of it, you will get a et hat multiplied by en hat, and this will be equal to 1 by rho, and this will be, according to this relation, this will be eb hat, and the magnitude of eb hat is 1, so it will be 1 by rho, and hence this is true. Okay, so that's why this statement written in black, 1 by rho is equal to modulus of dr by ds cross d2r by ds square is true. This would be called as equation 1.23. Okay, so another definition being thrown on your way, the plane of et and es, okay, et and en, sorry, the plane of et and okay, T and En at P is called oscillating plane. Okay, so let me just visually show sorry. Just use another ink. I'll use a red one this time. So the plane of ET and En is called the oscillating plane. So I'll just draw it something like this. I'll call this as plane of ET and En. So these are two vectors which were perpendicular to each other. So clearly they will form a plane. Okay, and this is called the oscillating plane. Okay, let's go back. Okay, so we will now also prove something which is relevant to this. Okay, it can be shown to be, this oscillating plane can be shown to be the plane through P which is closest to the trajectory. Let me now draw another diagram, this time slightly less complicated than the last time. Okay, so that's a good relief. Okay, so you have this again, the path. This is the point P of S, and you have okay, so this is the center C. Okay, not exactly the center. Okay, center C. The En is directed towards this all the time, and we always write it as En of S because it's valid at this point S. Okay, and then the radius of curvature is rho. Okay, so En again here is the principal normal which is directed towards this. Okay, now let me take another point which is over here. That point is P dash of S plus delta S, and then let me take another point like this which is P star of S plus delta S, and let me show that another circle, which this dashed circle, which is clearly a bigger circle over here. So this is the circle through P dash P star. This is the circle through what P and P dash. Okay, and obviously there's a frame F, point O. This is how you measure the position vector R of S. Okay, so okay, so let's see. Consider another point P star at S plus delta S1. Okay, so P star is another point at S plus delta S1, and P dash is clearly at S plus delta S. So a unique circle passes through P dash and P star. Let me make that statement. P dash P star. Okay. You should be able to verify this. Perhaps in your school you had done this. That find the equation of the circle passing through point 1, point 2 and point 3. Okay. So it's a similar sort of a claim which is being made over here. That there is a unique circle which passes through this. Verify. Okay. You may have to revise what you had learned back in school for this. Okay. Now see the radius, the center and the plane of the limiting circle. So this is called the limiting circle. I'll explain why we are calling it as a limiting circle. The radius, the center and the plane of the limiting circle through these points let me call it limiting circle. Okay, so limiting circle meaning the limit of this delta S and delta S1 is coming to 0. The radius, the center and the plane of the circle through these points as delta S tends to 0 and delta S1 tends to 0. Okay, so this point now is being brought close, this point is now also being brought close, and so on. Okay, so let me just remove this statement. I think this is not conveying what we want to convey. Okay, so the limiting circle is in this solid ink. Okay, delta S1 are the radius of curvature, center of curvature, and oscillating plane. P. Okay, it is the circle that best fits the curve. Which curve? This curve. Okay, at location S. So how did we do? We drew 3 points on this trajectory, P, P dash and P star. P was located as S, P dash was located at S plus delta S, and P star was located as S plus delta S1. Okay, Then we had a circle through P, P star and P dash, which you can see as a dashed circle on your screen. Now we claimed that if the limit delta S1 tends to 0, if the limit delta S tends to 0, both of them, okay, then you will get this so-called limiting circle shown in this solid lines or solid black line, and then the radius of such a circle will be the radius of curvature rho, and the center will be C, the definitions which we have just seen above, okay. And since it's the direct En is directed towards the center, this direction vector is also defined, okay. And hence you can say that this circle best fits the curve at this location S, okay. And that is the claim which we started out to make, that it can be shown that the plane through P which is closest, the plane, it can be shown, this plane, okay, can be shown to be the plane through P which is closest to the trajectory, okay. So this radius, the center and the plane is all of this, okay. So there is only one unique one which is over here. I mean, this point is obvious, but you should be able to think about it and agree, okay. The oscillating plane for a plane curve is the plane this is obvious, okay. The oscillating plane for a plane curve, meaning a two-dimensional curve, is the plane of this curve itself, okay. But for a spatial curve, which we are considering in our case, so all the fun happens only at the three-dimensional level, okay. So that's why we are studying all these things in 3 dimensions. But for a spatial curve like the one which we have drawn, it will change. It changes for different locations. Yes, okay. So now that we have defined all the so-called position coordinates, it's time to, just like for the previous cases, define the velocity and acceleration and the components of so on, okay. So we'll be utilizing this 1.22 a lot, okay. For example, to write the velocity, we will say that velocity is equal to dr by dt, okay. And let's see how we proceed by this. So we want to say, remember the topic of this study was kinematics of a point in path coordinates. So now this point, this material point which is of interest to us, we want to define its velocity. So the velocity is this. Again, it can be written in this form. Okay, and if you look at this term, you can call it S dot, okay, and you want to now see what dr by ds is. So let's go to equation 1.22. Let's go to equation 1.22. dr by ds is actually equal to et hat, okay. So I'll just write it as et hat over here. There you go, et hat. Okay, so this is the expression which we have for the velocity. Similarly, the acceleration is what? It is v dot. This will be equal to, now we want to use the chain rule over here. That will be s double dot et hat plus s dot et hat dot. Okay, now we will write this as s double dot et hat plus s dot det by ds by dt. Okay, this particular term can be written as s double dot et hat plus s dot whole square. Why? Because this is also s dot, right? Okay, so s dot whole square into det by ds. Now if you remember, det by ds is equal to actually en hat by rho. Let me show that. Okay, you should actually pause the video and see yourself, but I am doing it now since we are beginning to learn this course. Over here, okay, det by ds is equal to en hat by rho. So that's what we have written over there. Okay, so this is the acceleration, and the velocity was anyways written as s dot et hat. So this is 1.24 for you, the acceleration and velocity in terms of the path coordinates. Now we want to break them down into tangential and normal components. Okay, because it has these two components. So Vt, velocity, the tangential component is clearly s dot, okay, because it's like this, and the normal component will be 0. Vb will also be 0. Okay, just like velocity should have been actually written as s dot et hat plus 0 en hat plus 0 eb hat. So that's how we write this, and then you can clearly say that the magnitude of V okay is equal to, sorry, the value of V is equal to s dot 1.25. Similarly, you will have the tangential acceleration as s double dot equal to Vt dot, because Vt is equal to s dot. Then you will have the normal component of s dot whole square by rho Vt square by rho. Okay, and AB will be equal to 0. That would make the magnitude of the acceleration as s square, s double dot square plus s dot whole to the power of 4 by rho square. This is 1.26. Okay. Okay, so the last statement which can come out of it is very clearly writing V is equal to this V now, or is what we are using, okay, is V T E T hat acceleration is equal to V T dot E T hat plus V T square by rho E n hat 1.27. So if you look at the acceleration over here, is it possible to conclude that at a given s, the acceleration is in the oscillating plane? Remember, the oscillating plane is the plane which contains Et and En. Okay. So since the acceleration is written in terms of Et and En and not in B, there is no B component. Okay. That's why we say that at a given s the acceleration is in the oscillating plane. So this comes from this equation 1.27. Okay. And then some of the claims which can be further made about this result is that the tangential and normal components of the acceleration arise due to changes in the magnitude and direction of v. So the tangential component of acceleration is this. Okay, it arises due to a change in the magnitude and direction of v over here. So if this was not changing, okay, this would not come in. Similarly over here, so if Vt is not there, this won't be here as well. So at some place it's the magnitude, at some possibility it's the direction, but both of them have to. So this is a statement perhaps which you should verify yourself. I will write in red so that it catches your attention when you see this. The tangential and normal components of A arise due to changes in the magnitude and direction of V. So when you say a vector is changing, it automatically means that the magnitude and direction both can change, or one of them. Okay. So there are some other conclusions which you can make out of it. Look at the normal component of the acceleration. The normal component of acceleration. What is it? Vt square by rho. Okay. This is always greater than equal to 0 since it's a squared element and rho has to be positive. Okay. And it is directed towards C, right? Because this has a direction En and En is always towards the center of the circle. Over here, okay. So En is directed towards the center of the circle and hence the normal component of the acceleration is directed towards the center of curvature. Okay. Now if you look at, let me just bring that up. Okay. If you look at Vt is equal to S dot. Now this equals the magnitude of V if S dot is greater than equal to 0, and this equals magnitude of V should also come in. And can I bring in the same frame? This is the magnitude of V. Okay. So this equals minus V. Sorry, the screen is behaving a little funny today. This equals minus of V if S dot is smaller than 0. Now for a rectilinear motion, what is the radius of curvature? First of all, what is S? S is the coordinate along straight path. We called it by X, and rho will be equal to infinity. I think just call it tending to infinity, and the normal component will be tending to 0. Okay, just because the normal component is Vt square by rho. So if rho is tending to infinity, the normal component will tend to 0. So let's just make another definition of a speed is defined as the time rate of change of the distance moved along the trajectory relative to f. F is the frame through which we measure all these things. So speed is equal to s dot magnitude of the time rate change of the distance, and that would be equal to v, also like this, also like this, and also like this. Okay, all of these definitions you can see from up above, like 1.22 I guess. Yeah, so Vt is equal to s dot. So this can be called as 1.28. If you want to find the distance moved with respect to the frame f from time t0 to t, then you can have the distance moved okay. So this can go from t0 to t. See, notice that this s does not have a vector sign. Okay, it was because s was position. ds represents a small change in the position. Okay, and its meaning is very clear when you look at the circle which I had drawn. Okay, so this should become s dot dt. Okay, and just by writing ds by dt into dt, and that should be t naught into t, and s dot is the velocity dt. Okay, this is 1.29. So the displacement can be said as what's the position at rt minus what's the position at the t naught. Okay, and this can be related to the velocity by saying that since the velocity is equal to dr by dt, so just integrate that relation to get in dr is equal to v dt, and hence delta r is equal to the integral of v dt. So this is equation 1.30. Okay, now one of the last things which we have been doing in Cartesian and in cylindrical systems as well is the parametric definition. Okay, so we'll do the same over here. If the trajectory I hope you can notice that the coordinate system En and Es is not actually fixed a priori, it is moving with the particle, and this is very important in fluid mechanics. Okay, where you have to say follow or a bird, for example. Okay, you want to follow the path of a bird which is flying, you attach your origin to it, and the coordinate system has to be aligned, and it can keep on changing according to the path which it follows. It will obviously be following a three-dimensional spatial path. So this is different from the Cartesian or the cylindrical systems. If the trajectory is given parametrically as r is equal to r of tau, then Et will be clearly Et was found to be dr by ds, okay, and hence this would be true. This is according to equation 1.22. If you don't recall, please pause the video and go back and check that Et can be written as dr by ds, and this can now be written as dr by d tau and d tau by ds. This can be written as dr by d tau and d tau by ds. Okay, and this is equal to 1. Why is this equal to 1? Because the magnitude of this unit vector is 1. Okay, so this would imply that d tau by ds is actually equal to 1 by dr by ds, d tau, sorry. Also, since dr by ds is equal to, we can write it like this. We have just done that anyways. We can take a double derivative. Why are we taking this double derivative, by the way? Because we want to find En. Okay, En, if you check in equation 1.22, is equal to rho times d2r by ds square. So that's why we have to find this d2r by ds square. We'll be using the chain rule. d2r by d tau square d tau by ds whole square plus dr by d tau d2 tau by ds square. Okay, so that's how we have used the chain rule over here. Let me just check. Okay, why should I do like this? Okay, this is much better. So you have d2r, okay, correct, and d tau by ds. So this particular is okay. Okay, fine. So using this, you should be able to get this. Now using equation 1.23, where you have to find the radius of curvature, that is what, d2r by ds square, or that was actually equal to dr. We have shown all this in 1.23. Please go back and check if there is a doubt. Okay, now this is written as d tau square d tau by ds. Okay, So I hope you can see how we have used this term, okay, between dr, between d tau and ds, and dr and d tau. Okay, this should now be equal to dr by d tau cross d2r by d tau square, and this is divided by, okay, because of this now this is equal to dr by d tau cube. This means, and dr by d tau is the velocity, and d2r by d tau square is the acceleration, provided that the parameter tau is equal to time. Okay, so I should be very specific about this. I'll just write it like this: when tau is equal to time, when the parameter tau is actually equal to time, then you can write this. Okay, otherwise you can't, otherwise it is still just a parameter. So this implies that rho is equal to this is 1.31. So let's see how rho depends on. Let's make this claim in red. Rho, which is the radius, rho at S depends only on the shape and size of the trajectory and not on how fast the point moves over it. Well, if you just look at this final expression, it seems it's depending on how fast it's there, but understand this definition and convince yourself that what is written as red is actually true. Okay, and the way to go about it is this: put expressions for velocity and acceleration in 1.31. okay, in this equation, velocity and acceleration, where will you put it from? From equation 1.24252627, okay, or 1.27 to be specific. So 1.27, you put this over here and see that it's an identity independent of S dot and S double dot, and since it is independent of S dot and S double dot, it will be shown to be not depending on how fast this is moving. Okay, so that is done, and we have some small further discussions which are just based on what we have learned now remaining. So let's see how we can address them. So if you want to say find the if you have the acceleration given in terms of time or in velocities, how will you say find the time which was taken to reach from this situation to that situation and so on. So let's see how all that can be done. Quite straightforward according to me. So it always requires a black ink first. So the following equations are used to obtain Vt and Vs by separating the variables is something I think you have done. This was done for integration. You must have done it in your school. Okay. So if you have, say, the tangential acceleration, this is dv t by dt. Okay. This is something which you can actually find out that at is equal to vt dash. This was equation 1.26. Please go and check. Pause the video and go and check. You had already done that. So once this is written, then you can say that Vt minus Vt, sorry, of 0 is equal to 0 to t, At of t dt, and then you can write it in time also, that the time will be equal to Vt of 0, Vt of t, 1 by At Vt dvt. Okay, you have to just change the what your integration is over. Okay, this is coming, by the way, from over here directly. Okay, now if you write the At in terms of path coordinates, okay, here you have At and t and At of Vt. If you have At over this S and At over Vt, okay, then you can say At is equal to dVt by dt. This is again coming from equation 1.26. This means you have dVt by ds, ds by dt, and ds by dt is actually equal to Vt, and this will be dVt by ds. So you can perform the integration by easily saying that Vt square, okay, if you integrate At, okay, you do a At into ds is equal to Vt into dVt, and then you integrate both sides. At clearly now is given in terms of s, okay, hence you can integrate that. So you will get Vt of s whole square minus Vt of 0 whole square is equal to 2 times of 0 to s At s ds, okay, and s would be equal to Vt of 0, Vt of s, Vt of At, Vt dVt. Okay, now for if the velocity is given, say, in terms of s and time. Then how to go about it? Again, Vt is equal to ds by dt. That's coming from equation 1.25. Okay, now you can do an integration and write that st minus s of 0 is equal to 0 to t v t t dt. Okay, and time is equal to similarly s0 st 1 by vt of s ds. So this is 1.3. So in whichever form you are given, you should be able to do the respective integration. Okay, this is the whole point of this. Okay, let me just now. Okay, so all these integrals which you see over here, this one, I mean, if it is easy to integrate, you integrate it using the methods which you already know. If not, then you can use some numerical methods, which perhaps is something which you will learn later in your studies. That for some things which are not easily integrable using the formulas which we know, you can go for numerical integration. I mean, the idea is the same. I mean, if there is a function which you don't know about, and then you have to find its value, and somehow you are not able to integrate it, okay, one reason or the other. So what you do is you just break them down into separate small parts and do it. It's an approximate method because you miss out certain parts of it, but it still works reasonably well. I mean, if the number of partitions which you make are large enough, then the answer which you get is close enough to the actual answer. So more details would come whenever you study about numerical methods later in your studies. So if you have a uniform tangential acceleration, at of t is equal to a naught, it's a constant, okay, then all these equations 1.32, 1.33 and 1.34, what would they become? So 1.32 will become Vt, 1.32 will become Vt minus Vt at t minus Vt at 0 will be equal to a naught at t, okay. So that would become Vt of 0 minus equal to Vt at t. And then S of t if you look at 1.33 over here, okay, I think that you are able to see. So S of t will be equal to S of 0 plus Vt of 0 at t plus half a naught t square, okay. And then the last, which is 1.34, sorry, this will come because of this 1.34, okay. It's somewhat obvious as well, but it should come from over here, okay. And then the last is coming from over here, which is 1.33, that would be Vt of s whole square minus Vt of square 0 equal to 2 a naught s. This is 1.35. Okay, so for a uniform acceleration, these are the formulas, and I hope that these are something which you can immediately recognize, okay. Perhaps it took a much longer time and a lot of maths to come to this in this course, but I think you recognize it from your earlier studies. Okay, now let's see some simplifications for a plane trajectory. I mean, it's a 2D path. Okay, let me show that. Let me show. Okay, so you have x and you have y. So at a given point P over here, okay, so let's just say that it's an x comma y and this is the path S. Okay, you can say that R, any position of P, okay, over here will be clearly R. So R will be equal to xi hat plus f of x j hat. Okay, so for this particular case, rho is obtained tau equal to x in 1.31. 1.31, if you remember, was rho is equal to this one. Where did it go? Over here, sorry. Over here. So you put tau is equal to x. See, tau was a parameter. It was put as time when you were trying to write this, but you can put it as tau equal to x and then you would get the rho. Okay. So we can do a dr by dx is equal to I hat plus f dash of j hat. So f dash is the d by dx is okay. So this is over here, and then sorry, you have d2 r by dx square is equal to f double dash of j hat. Okay, because this, if you derive it with respect to x, will become 0. Now dr by dx modulus would be equal to 1 plus f dash square 1 by 2 d2r by dx square is equal to f double dash magnitude. Okay, now if you use 1.31, one will get as 1 plus f dash square 3 by 2 f double dot magnitude. Okay, so this is 1.36, and it should not be very hard to visualize this. At this point, ET is this, En is this. Then over here the double derivative is positive at this point. Okay, so you will say that f double dash is 0, is greater than 0. Okay, and this clearly is, needless to say, y equal to fx. It's obvious. Similarly, now when you come, okay, say at this particular point, this particular s, you will have a En, and again there will be a center, then there will be a tangential t hat, and at this particular point f double dash will be smaller than 0. Okay, the same will happen, say, at any third point. So you already know about this first and second derivative test, especially for a plane. Okay, and here again f double dash will be smaller than 0, so it shows a somewhat of a inverted curve. Okay, so this is how you get the rho, and you can see that both the single and the double derivative of this trajectory play a role in defining rho, not how fast the particle, the point is moving, not the particle. Okay, you can also say in this graph that tan, let me just say it, I should say it, so tan of psi is equal to dy by dx. Okay, so if this is your angle psi, so the slope dy by dx is equal to this, and this, as you already know, is written as f dash. Et again is written as cos psi I hat plus sin psi j hat. And then you have equal to minus sin psi of I hat plus cos of psi j hat d psi by ds. That would come just by integrating this with respect to s. Okay, and clearly 1 by rho would be det by ds equal to d psi by ds. Okay, so this is coming up because of 1.23. okay, this has come up because of 1.23. now the normal vector En, as you know, is equal to det by ds modulus of det by ds. Okay, it's in the direction of det by ds, and its magnitude is rho times of det by ds, that is coming from 1.22. okay, please pause the video and check all these things. Don't just assume that it should be very clear just by looking at it. Okay, now once you have this, you can substitute det by ds from over here. Okay, and divide by the magnitude of det by ds, which is this one. Okay, so overall you should get minus sine psi I hat plus cos psi j hat d psi by ds divided by d psi by ds equal to plus minus sine I hat plus cos psi j hat. Okay, so this is what we get for En, and that is how we are getting this En vector, the one in greens which you see over here. That's how we have drawn all this using Et. Remember, we always draw the tangent first, like we did with that circle also. Okay, and we are doing the same here, tangent first and then the normal or the unit normal directed towards the center of the curvature. Okay, so clearly out of this you know that the positive sign over here will be used. Let me just write it over here. En, I will write in some other ink. Okay, no, hold on. So just let me write this En which we have derived over here. So En would be written as what? Let's see. It's En will be written as plus minus sine psi I hat plus cos psi j hat. Okay, so the positive sign over here for the normal will be used at this point P over here. Reason is that d psi by ds is greater than 0, and negative sign will be used over, say, this point over here Q and even R, because over here d psi by ds is smaller than 0. Okay, and obviously it goes without saying that all these normals will be directed towards the center. So d psi by ds, this sign is determining what to put. Okay, basically this has become plus minus over here. Okay, so if you interchange, so in this analysis which we have just done, if you interchange x and y, in the previous analysis, okay, we would get rho is equal to 1 plus dx by dy 3 by 2 d2x by dy square. This is equation 1.37. Okay, now here is a question with which I would want to finish this particular topic. What questions are in red? What does it physically mean to interchange x and y you should think about it, that in a situation when this is interchanged, what does it physically mean? Okay, if the path is like this, what would be the path over there, and so on. Okay, so with this I think we can give an end to this topic. We now discuss the concept of relative velocity and acceleration. Obviously this is all with respect to a material point. Okay, so let's see the the definitions of it. We define relative position vector RPAF relative velocity V PAF and relative acceleration of a moving point P relative to a moving point A in frame F. Let me first draw a diagram. This is a frame F. This is the point P. This is the point A. This is RP. This is RA. And this is, this is RPA. So we can define them as RPA of F. Do note over here that all the points, I mean this P and F, are all moving points. Okay, both P and A are moving. So RPA of F is equal to RP of F minus of RA of F, and similarly the relative velocity is RPA of F dot, that would be equal to RP of F dot minus RA of F dot is VP of F minus VA of F. This is 1.39. Then the relative acceleration PA is again the time derivative of the relative velocity. This would make it V dot PF minus V dot AF equal to acceleration of P minus acceleration of A. This is 1.40. Okay, so we can now, let me just this is a frame F. and then you have this other point B. It can also be another moving point. So this is RB, this is RP, this is RA, this is RPA, this is RAB, okay, and then you have this, sorry, this is RPB. You may have another point C, you may have another point S. So we want to find the use the chain rule, okay, and find the relative positions and velocities and accelerations. So let's see. Straightforward, as you can see, RP will be equal to RPA plus RA, okay. Then you can have RP is equal to RPA plus RAB plus RB. Okay, you can just use the suitable vector triangles and you will find all of this. Then you can lastly have RPB is equal to RPA plus RAB. Okay, so in this case you will be choosing RPB, PA, PB. Okay, so you will be choosing this, and this. Okay, so it's all straightforward vector addition. Okay, similarly the relative velocity, so this is combinedly, okay, let's write all of it. VP is equal to VPA plus VA, okay, just by a derivative of time for this expression, okay, we can write this. Then VP will be equal to VPA plus VAB plus VB, and similarly you can finally have VPB is equal to VPA plus VAB. AP is equal to APA plus AA. Again you take a time derivative of this one, okay, and similarly the acceleration of P is equal to APA plus acceleration AB plus AP, okay, and lastly one can write APB is equal to APA plus AAP. So this is important, perhaps say in a machine where there are many parts moving with respect to each other and you have to define the relative velocity or the acceleration of one part with respect to the other. Okay, so at that point such a chain rule will be necessary, and you can keep on extending this. I mean, it's not just now OAB, okay, you can say have this point C and S also into the picture. In that case you can have APS is equal to APA plus AAB plus ABC plus ACS. Okay, So this is all equation 1.41. Okay. So there is also this concept of a rate of separation and rate of approach, which we can just see. In terms of the relative velocity gives you that answer. So let's see what that is. The rate of separation of points A and B, A and P, sorry, A and P is the rate at which the distance D is equal to AP between them increases with time. The rate of approach being its negative. Okay, so I hope that brings us to this rate of separation and rate of approach. Okay. Now we have already seen this. Okay, put that in red. We already know that the distance D equal to AP measured at a given time is the same for all reference frames. Okay, now I say that we already know, but at this point you should be able to recall how do we exactly know that this distance will be the same in all reference frames. Okay, if you cannot recall, you have to go back to these discussions which we have had and find out that exact place where we show that this distance D at any given time will be the same for all reference frames. Okay, this implies that the rate of separation d dot, okay, time derivative and its derivative d double dot are independent of reference frames. So how do we find d dot? Let's see. D over here can be said to be d square is RPA dot RPA. Okay, you can see what RPA is. It's the relative separation between the point P and A, this one. Okay, so the distance between square, or the square root of the distance, is d square is equal to RPA dot RPA. Now one can apply, differentiate both sides of this with respect to time. We would have this and then apply the chain rule of differentiation. VPA Okay, now t dot will be equal to VPA dot RPA. Why would that be true? Because this is the same as this. Okay, and hence dd dot will be equal to VPA dot RPA. This implies that d dot is equal to VPA dot EPA. Okay. So clearly we have written that EPA is equal to RPA by D. Okay. Now we want to differentiate this once more, this equation with respect to time. So we will have a d double dot plus t dot square is equal to APA dot RPA plus VPA dot VPA. Okay, so this has been differentiated with respect to time, and with this we have got that d double dot is equal to APA dot EPA plus VPA square minus d dot square divided by d. Okay, so basically this has been taken to the other side, okay, and divided by d. Okay, both sides have been divided by d. So with that we can say that d dot is the component of VPA in the direction of RPA. Okay, so EPA, as you know, we have already written what, you can just refer to what we have written over here. But d double dot is not the component of APA in the direction of RPA. Sorry. Okay, so d dot is the component of VPA in the direction of RPA. Okay, you can see that using this. And then d double dot is not the component of APA, so it was not adding up like that. That you can see because it's slightly, I mean, had this term not been there, you could have said that d double dot is the component of APA in the direction of RPA, but because of the presence of this term we cannot say the same. Okay, so we'll now be moving on to this topic of rectilinear motion. Okay, so this is perhaps the easiest to understand. For this, you know that we choose the x-axis along the path, so s is equal to x. Choose x-axis along the path with s is equal to x. In this section, and the next. So the velocity and acceleration along I hat will be denoted by V and A. Okay, so let's see, the position vector at is xi hat. The velocity over here, what was velocity? If you remember, it was s dot, but since s is equal to x, it will be x dot I hat. Okay, and I dot will anyways be 0, so that's not coming up. And then the acceleration will be x double dot I hat equal to v dot I hat equal to a I 1.42. So v is equal to x dot is equal to s dot equal to vt. Okay, this is coming from the path coordinate discussions which we have had. If you do not recall any of them, now is the time to pause the video and go back to the path coordinates and then see, for example, how is this s dot equal to vt. Then you will have the acceleration is equal to x double dot is equal to v dot is equal to v dv by dx. Okay, and this will be equal to s double dot equal to at. Okay, can you recall this? It's a question mark. Okay, if the answer is no, now is the time to go back and revise and then come back and see if you can answer this. Okay, sorry, 1.43. Sorry. Okay, so let's say that let's call the speed, and this is somewhat of a clarification, that the speed and magnitude of acceleration are not not v and a, but v and a. Okay, so it is needless to mention that if the a and v have the same sign, okay, so it's not the speed, because a and v can have a sign over here, right? Because that sign can come because of this time derivative. So a can be negative if the time rate change of velocity is negative. Similarly, v can be negative if the time rate change of position is negative. So that's why the speed and magnitude of the acceleration are not v and a over here. Okay, so you already know that if the velocity and acceleration, if a and v have the same sign, then the speed will increase, and if they have opposite sign, then the speed will decrease. That's called deceleration. Okay, so if a and v have same sign, then the speed v increases This is called acceleration. If A and V have opposite signs, okay, then the speed V decreases. This is called deceleration. Okay, so A in general, if you look at A over here, this one, this can be a function of this is anyways equal to x double dot, and this can be a function of the position, the v, and time. Okay, this is generally, okay, this is 1.44. So in a rectilinear motion, A can be a function of x, v, and t. This is the most general case. So if you have to say now integrate this, if you have this as a function given, okay, I don't know, maybe x square plus t by 2 or something like that, and you want to find the position, you will have to clearly integrate this, because this is d2x by dt square, and then you will have to integrate this twice. For these two integrations to happen, you will need two initial conditions. Okay, so once these conditions are known to you, you can go ahead with the integration, and that can be, say for example, t equal to 0, x0 is equal to x naught, and it's called an initial condition because we know it at t equal to 0. And similarly, x dot, I shouldn't call it v, I should x dot of 0 is equal to v naught. So these are the two initial conditions which can be used to actually solve this. Okay, it could also be that two initial conditions are not there. Okay, but say you have at t equal to 0, x0 is known, and at t equal to t1, x of t1 is known. Okay, so this may be called as the conditions at the two ends of the boundary of time. Okay, so either of these two things can be used depending on what is given in the situation or what is known a priori in the situation. So the point is that you will require two conditions for this to be solved, for this to be integrated. Okay. Okay, now if a is known function of only one of the variables, then this equation 1.44 can be integrated quite easily. Okay, for example, if it is a function of only, I don't know, x or v or time, then it's quite easy to solve all that. Okay. So for example, we had studied these relations 1.32, okay, and we had in the path coordinates. So you should please revise that over here, because all those equations will hold true over here. Okay, if a is a function of only one of the variables. So derive, I should write in red. Derive the following using 1.32 to 1.35. This is something which you should be able to do. Don't assume that what I am writing below is obviously known to you. Okay, you should be able to derive this. So you have to do and show that v is equal to dx by dt using the path coordinates. Okay, I am aware that they will sound very familiar to you, but you have to be comfortable with the path coordinates, and hence requesting you to do the same. Remember, slope of xt curve, it is coming from the slope of the st curve, okay, because s has been taken as x in this case. So this will be the slope of vt curve, okay, and delta x is equal to x of t2 minus x of t1. This is the area under vt curve, and similarly delta v is equal to v of t2 minus v of t1 equal to a dt t1 of t2. This is the area under AT curve. Now you can consider a situation where some part of the velocity or acceleration was positive and the other part of the velocity of acceleration was negative. How then would you find the distance? Okay, so the area in half plane of positive v in vt plane and of positive a in positive and of positive a in AT plane is considered as positive, and the rest is negative. Okay, and why would area be needed? To obviously calculate the distance or the change in velocity depending on which graph you are looking at. So the distance d12 is the distance traveled from time 1 to 2, that is equal to t1 to t2 modulus of v dt is equal to sum of magnitudes of area under vt curve. So do the positive and negative parts separately and add the values without considering the signs. That will be the distance. Okay, but for displacement you can already see that you should have derived it using the path coordinates as just the area under the curve. Okay, so the this idea of rectilinear motion is not new to you. Okay, you should have known some of these situations. So let me just like take up one of them. Okay, so you have this pulley. Okay, and you have this weight B on an incline. It's moving down with VB and AB. This is the path coordinate SB. This is the path SA. This is going up with VA and AA. Okay, so we have inextensible cables, meaning that cables cannot extend. Okay, and in this situation what would you have? You would have SA is equal to SB, you would have VA is equal to VB, you would have AA is equal to AB. Okay, so this is how a rectilinear motion can be seen, and it is perhaps when you do your course in workshop practice and say you do your fitting experiment, fitting okay, so this normally is a part of workshop. So what you have to do is you have to have a workpiece, and it is fixed between so-called vice. Okay, and the way you fix it, this is the workpiece over which you will be trying to fit two parts. Maybe you will have to file some part out of it. Okay, and to fix it in the work in the between the vice, you have to have a rotatory motion, and this particular vice which is moving will actually move in like this in a rectilinear motion. Okay, and that's the concept of most of the screws and nuts and bolts as well. See, any screw which you have, okay, it will have all these threads, and then you will put a screwdriver, okay, and then you will rotate it, and then this will move ahead. Okay, similar with a nut and bolt. So if you have this bolt like this with all these threads, and then there is a nut like this, the nut has to keep on rotating. Eventually it moves rectilinearly in this direction. Okay, so we had already seen some of these examples before, but I think now it is clear that rectilinear motion itself does not necessarily mean that there is no rotation. Okay, so if you see, the center of mass of this bolt will continue to move ahead. Okay, so these are some examples, and depending on your choice of discipline, you will be reading or using one of them more than the other. Okay, so that is where we can end this discussion on rectilinear motion.